about first order logic with counting. So the starting point is that, okay, first order logic is the logical core of SQL. We all agree on this somehow. But one important aspect that is missing in first order logic is the ability to count. So in many database queries, we want to count or take averages or things like this, which are similar in spirit. And here's just one example that we'll pick up once in a while. So we have a customer database, and we will basically want to count how many customers we have from each country, right? So that's the fairly simple query that uses counting, and there's no way we can express this in first order logic. We don't even have the type of variables we would need to express this. So we completely fail there. Similarly, now that's a useless query, but it's still a good example for many things. A query like a relation contains an even number of tuples. That's a Boolean query, and we know that it's not expressible in first order logic. It is, don't you think? I mean, don't ask me to write down the SQL expression, but I think it is. I think, okay, we don't have to figure that out. Okay, so we want to look at first order logic with counting, and in a particular query evaluation for first order logic with counting. Now, first order logic with counting in various variations has been around for a long time. So we use one formalization here due to Nicole Schweikart and Dietrich Kuske, which I like, and expressiveness is somewhere in the middle, I think, of all the variants that are considered, but it goes as follows. So we fix a set of predicates on the natural numbers. This could be something like equality, or less than would be binary predicates, or something prime, or something completely esoteric, like x to the 7 equals y to the 5th minus 4, whatever we want, basically. Okay, can be something undecidable, we don't care. It's just a set of predicates, and then we build our first order logic with counting around this. Basically, we add counting terms, which just count the number of tuples satisfying a particular formula where these variables appear. And then we also use integers as constant terms, and we can combine terms. We can build polynomials basically using all these terms. And then we can put the terms into the predicates from our set. Okay? And with this, that's basically the logic. I'm not going into any details of how it's built, but I think you can imagine. In this form, it was introduced, as I said, by Schweikart and Kuske, but similar counting logics have been around for a long time. And there's also variants where you can quantify over counting over the numeric side and things like this. But I like this better because you don't have to worry, you don't have to think about how large your numeric universe is and things like this. So I like this formalization. It's clean and simple and easy to work with. Yeah, I think in the paper by Nicole and Dietrich, there are some reasons why it's good to have them in this form. You could probably also add other functions or only predicates. Yeah, it's really not important for us here. And I don't think it's important in anywhere. Okay. So, for example, this even thing we can now express, we use an even cardinality predicate, and then we just count the number of tuples in a relation and say it's even. Okay, so that's easy. The other, the SQL example, can also be expressed. So basically for this query, we would have to write it like this with two variables where we have the country variable here and there is a numeric term that gives us the number of customers, and then you can just write it down. This is in a way this grouping thing. We go over all customers for all countries which have at least one customer, and here we count the number of IDs for this country, which is a free variable. So things like this we can express in this logic. Okay, and now we want to look at query evaluation. And so query evaluation just means we're given a query of some query language. In our case, it will be this first order logic with counting. Possibly, well, and we're given an instance. Possibly the instance is restricted to come from some class of instances, and then we can think about the complexity, and we have this standard classification. Okay, let me just fix this notation. N is always the database size, K is the query size, and sometimes there's an F appearing that's just an arbitrary function. Okay, so maybe the most natural complexity measure would be a combined complexity. That is, we want a running time for a query evaluation algorithm that is polynomial in the input, that is in K and N. But we can rarely achieve this. Then we're all used to data complexity here, which means it's polynomial time if we fix the query. Somewhere in between is parametrized complexity, which can also be regarded as fixing the query, but then we don't want the exponent of the polynomial to depend on the query. Okay? So that is nice because it's consistent with a high complexity, but can still be useful as long as this function is reasonable and the polynomial is reasonable. And that's, of course, always the case for distractibility. And yeah, I've been working on this for a long time, as you may or may not know, and I've looked in particular at first order logic and try to understand on which classes of structures it's fixed parameter tractable. Okay? So first of all, in general, it is not. So the evaluation problem for Boolean first order queries is complete for a parameterized complexity class called AW star, and that means it's unlikely to be fixed parameter tractable. Let's just leave it there. But now if we restrict the input instances, it can be tractable. And yeah, that's what I've looked at. In particular, I've looked at sparse graph classes for a long time. So here's a picture of sparse classes. And the most general notion of sparseness that is kind of still good in a way is this nowhere dense. Well, we could say bounded average degree means sparse. That would be reasonable, but it wouldn't work very well because a structure can have bounded average degree but be very dense in a small part, say of size square root of the whole structure, and that's and completely sparse, no edges anywhere else. So the average degree would still be low, but that wouldn't buy us anything. Then we can say, okay, we somehow must distribute this bounded average degree evenly, and there's bounded degeneracy, which does this to some extent, and then nowhere dense does it a bit more. And if you do this, so basically it makes sure that whenever you look at small substructures in a certain sense, the average degree will be small. Okay, so that's a reasonable notion, although technically complicated. And, well, it includes, for example, planar graphs, bounded tree width graphs, bounded degree graphs, and so on. That's what this picture tells you, and I've been talking about this for long enough. You have probably read it. So, what we have proved is that for these nowhere dense graphs, first order query evaluation is possible in almost linear time. That is in time n to the 1 plus epsilon for every epsilon. Okay, and now there's the factor depending on the query. which appears in all these results and is very large in all these results. Now, this factor is mainly terrible because the quantifier alternation, which automatically makes it non-elementary. It's not so bad because of the graph theory. So if you use things like graph minor theory, then you have another source of very large constants. For nowhere dense, it's not like this. So that makes nowhere dense in a way nicer. So you don't go through really horrible graph theory there. One has to say that. Okay, and one observation is that if we take a class of graphs that is closed under taking subgraphs, then this result is optimal. You can't go beyond this. Okay, and another result I want to mention is one that was presented yesterday, I suppose, is that we can even evaluate queries with free variables on nowhere dense graphs with constant delay. Okay. Okay, so we thought, why not do something like this for the counting logic? And actually, when we started to talk about this, when Nicole visited sometime last year, Nicole and Dietrich had already proved on bounded degree graphs, you get linear time fixed parameter tractability. So very nice. So we thought, let's extend this, at least to planar. You know, the thing I've been doing for the last 20 years, I can do this, only it turned out that it doesn't work. And so what we observed after a while is that the evaluation problem for these counting queries, even if we only have the equality predicate, is already hard over trees. And this, I think, is a result that is very simple to prove. I'm going to show you the proof on the next slide. But I think it's kind of good to know, in particular in view of the results for bounded degree graphs. So let me show you the proof. It's extremely simple. We reduce the evaluation problem on general, for first order queries on general graphs, which you remember is hard, to the evaluation problem for counting queries over trees. So we have a graph and a formula, and we want to evaluate the formula in this graph, and now we reduce it to trees. So first, we construct a tree from this graph, and it's a simple trick that we do. So the color coding is just to match things from the graph to the tree. So first of all, the vertices of the graph appear as children of the root in the tree. And then every vertex has a child for every edge going out of this vertex. So for example, for C, we have this red, green, and blue edge. So we have a red, green, and blue child. And now, for each edge, we just take a natural number, and that's the number of children that appears here. So, for example, blue means 2 children. So the color blue doesn't appear in the structure. It's just for illustration purposes. But the 2 children are the thing. Now, to say there is an edge between A and C, we say A and C both have a child with the same number of children. Okay, and that's the whole coding. So now we can just translate the first order formula in the right way, and using this cardinality quantifier, we have the reduction. Very simple, but I think I like this result. It's maybe the most relevant observation that we make in this paper. Yeah, you know. Okay. But of course, I like nowhere dense as well, so we didn't stop there. How much time do I have? So let me talk about nowhere dense for a few minutes. So the problem is really that we could destroy the locality of the logic by using this counting. We had these long distance interactions, okay? So then we were wondering, so how far, or what fragment of the logic still does work? And essentially what we found, what is a good fragment to look at, is one where we have these counting formulas. So some predicate from P and then a number of terms. We only allow them if they have one free variable. So we want to keep the counting local. Note that each of the terms may still count over long tuples. It's just that the interaction between different terms is supposed to be restricted to one variable, okay? So, for example, a formula that would be good would be this one, saying in a directed graph, the in degree of x is the same as the out degree, okay? So we have this counting predicate here. We have two terms related by this equality relation. Both of them have the same free variable x. So that's okay. And here's a formula that is not okay. It says that both x and y have the same in degree, because that's now a counting formula where we have two free variables, x and y. Okay, that's not allowed. That's exactly what we needed in the counter example on the last slide. The thing before is allowed. Okay. And also the formulas in the example I had on the, I think, second slide, they also work for this logic. So actually, in this fragment, FOC1, you can still express a lot of useful things. So I think it's a reasonable fragment to look at. Okay, and what we show then is that it inherits locality from first order logic. Basically, we show it's getting horribly complicated, unfortunately, but what we show is that we can somehow compose all formulas here from local formulas and what we call connected local terms. So local formulas, you know, that means the truth value only depends on a bounded radius neighborhood. And connected means that the variables, also the bound variables, the variables bound by counting quantifiers in particular, all are required to be close together somehow. And now with this normal form, we can then extend the nowhere dense results to these counting queries. Okay, so it's exactly the same result as we had for first order before. It can be extended here. A nice corollary of this is that we can also count the number of tuple satisfying formulas in nowhere dense graphs. And that was only known for planar graphs before for first order logic. Counting tuples is kind of important if you want to compute probabilities and all that. If you want to do any quantitative reason, then you have to usually do this. So that just falls out of our results because we have the counting terms there. And that's pretty much it. So we have these two results. One is the lower bound result, which is simple, but I think good to know. I showed you how this goes. And then we identified this fragment, FOC1, and could extend basically the results from first order query evaluation to this. Okay, and one thing we want to look at now is to extend the logics by richer numerical predicates, because I think that's something that is interesting in many situations. So for example, well, we can start with averages, but then we can look in general into terms going into the reals or in some vector spaces or whatever. I think in many situations that would be very interesting. Okay, and that's it. I don't know. I haven't thought about this. And you have to be careful. You have to identify the right things in the tree, and that I can't. No. No, I don't think it's two variables. Somehow that sounds wrong, because query evaluation for two variables is still possible in? I don't know. I really don't know. I haven't thought about it. It's a good question. I have to think about it.
Take FOC1.
Yeah.
What does it map to back in SQL?
Oh, I have no idea.
That was the original motivation.
No, yeah, but you know, I don't know what fragment it is. Yeah, that's okay. I can express my own propaganda queries. That's what I know. I don't know the exact fragment.
So FOC1 is some fragment of SQL. I think it would be interesting to at least tell us what fragment.
Yeah, basically, if you. So what are these counts predicates? First of all, you don't allow counting over longer tuples. You only count over tuples with so you only have one variable in the output, and you only, if you do comparisons, you would have only one free variable in this comparison. So if you write something like count this equals count that, then you would only allow one free variable. That's the direct restrictions. Now, of course, there are many other numerical things in SQL and other things here, and I don't know how exactly they map. But the crucial thing is when you work with these counting, with the results of counting, you shouldn't compare things that are
Take general FOCP.
Yes.
Okay, but define P to be the thing that somehow is standard, not
Yeah.
Does that really correspond to SQL?
No, it does not correspond to SQL. It can express certain things. From SQL, if you take reasonable counting things, it should be a subset of SQL, but I don't think it can express everything.
Allow you to extract. Now, of course, you take the SQL with PL, and then you can do everything. But the basic SQL, there is a limit where you can use the counts. So I'm not.
But it's basically it's first order, and then you do so you basically and then you can compare counts. Yeah, I would think you can, but.
There is also a mention about the flow and lower dense graph about enumeration. Also controlled here in the FOC1 or the whole enumeration?
I don't know.
You don't know that?
No.
Which kind of techniques do you use to prove these locality?
So basically, one insight we had is that you can use these counting terms to get rid of these basic local terms in Geifmann's. So we never have to say there are certain things that are far apart and satisfy something. That you can simulate by the counting. So then for first order, you easily can express first order using the counting terms and just local counting terms. And then we basically stratify this FOC1 logic, where we always replace the counting set terms by the normal form we get for the previous level, and we build up a tower, and that gets really messy, but on the other hand, you can maybe imagine that it works. So it's nice, just this thing that I also didn't know before, that in Geifmann you can replace these basic local terms by counting terms. Because you can always say, you count what is close together, so the rest must be far apart. This is, okay, it's not a revolutionary insight, but you know, that's what's underlying this. Yeah. No, it's basically, it's non-elementary, and that just depends on the quantifier alternations. So they can be arbitrarily deep, and you get one exponential for every quantifier elimination. There's also something coming from nowhere dense, but then you would have to go into the parameters that come from nowhere dense. So if you have parameters for the class, then probably that would be kind of exponential in these parameters, but it really depends on how exactly you parameterize your basic class.